Hi everyone, I'm Sunaina here presenting you about harvest yield and scalable tolerance systems. The contents are to be as follows: abstract, motivation, CAP principles, strategies, programming and uses of those orthogonal mechanism, and finally we are going to discuss about the research agenda. Going to the abstract of this project is of how the cost of accommodating consistency and state management with high availability is magnified by the uncommon scale and robustness needs of today's internet applications. For this, we propose two strategies for improving overall availability using simple mechanisms that scale over large applications whose output behavior tolerates delicate degradation. We indicate this degradation in terms of harvest and yield. Later, we are going to map it directly onto engineering mechanisms that enhance availability by improving fault isolation. Motivation, hypothesis, and relevance. Increasingly, infrastructure services not only hold routing but also application level assets such as search engines, adaptation, proxies, and web caches. These applications must resist the same operational expectations and exponentially growing user loads as the routing infrastructure and therefore absorbing equal amounts of hardware and software. The current trend of exploiting commodity computer clusters for scalability and availability is reflected in the largest web server installations. The scale of these applications is bringing the common trade-off between consistency and availability into very sharp assistance. We propose two general directions for future work in building large-scale powerful systems. Our approaches accept partial failures by emphasizing simple composition mechanisms that build up fault condition and by translating possible partial failure modes into engineering mechanisms that provide evenly downgrading functionality rather than lack of availability of the service as a whole. The paths were refined in the context of cluster computing. CAP principle. What exactly CAP stands for? Consistency, availability, and partition. Strong consistency means single copy asset consistency, whereby the assumption a strong consistent system provides the availability to perform updates, otherwise discussing consistency is irrelevant. High availability is assumed to be given by redundancy, for example data replication, which means data is considered highly available if a given consumer of the data can always read some copy. Partition resilience means that the system as a whole can survive a partition between data replicas. Strong cap principle. The cap formulation makes accurate trade-off in designing distributed infrastructure applications. It is easy to identify examples of each pairing of cap, outlining the proof by exhaustive example of the strong cap principle. First one, CA without P. Databases that provides distributed transaction semantics can only do so in the absence of the network separating server peers. Next is CP without A. In the event of a partition, further transactions to an asset database may be blocked until the partition heals to avoid the risk of introducing merge conflict. Hence, this is also inconsistent. Coming to the third one, it is AP without C. HTTP web caching provides client-server partition resilience by replicating documents, but a client-server partition prevents verification of the freshness of an expired replica. In general, any distributed database problems can be solved with either expiration-based caching to get AP or replicas and majority voting to get computers. The minority is unavailable. In practice, many applications are best described in terms of reduced consistency or availability. Harvest yield and cap principle. Both strategies we propose for improving availability with simple mechanism relies on the ability to broaden a nation of correct behavior for the target application and then exploit the trade-off in the cap principle to improve availability at large scale. We assume that clients make queries to servers in which two metrics of correct behavior. First one is yield, the probability of completing a request. Second one is harvest, measure the fractions of the data reflected in the response. As I said you, there are two strategies. First one, trading harvest for yield, probabilistic availability. What is exactly this? Nearly all systems are probabilistic. In particular, internet-based servers are dependent on the best effort internet for true availability. Therefore, availability maps naturally to probabilistic approaches, and it is worth addressing probabilistic systems directly so that we can understand and limit the impact of faults. Coming to the second one, application decomposition and orthogonal mechanisms. Some large applications can be decomposed into subsystems that are independently intolerant to harvest degradation, means they fail by reducing yield, but whose independent failure allows the overall application to continue functioning with reduced utility. The application as a whole is then tolerant of harvest degradation. A good decomposition has at least one actual benefit and one potential benefit. The actual benefit is the availability to provision each subsystem's state management separately, providing strong consistency or persistent state only for the subsystems that need it, not for the entire application. Traditionally, the boundary between subsystems with differing state management requirements and data semantics has been characterized via narrow interface layers. We propose that in some cases it is possible to do even better if we can identify orthogonal mechanisms. Unlike a layered mechanism which sits above or below the next layer, an orthogonal mechanism is independent of other mechanisms and has essentially no runtime interface to the other mechanisms. Since Brooks reveals that the complexity of a software project grows as a square of the number of engineers, and Levison cites evidence that most failure in complex systems result from unexpected intercomponent interaction rather than intra-component bugs. We conclude that less machinery is better. The ability to exploit orthogonal mechanism therefore constitutes a advantage of decomposition. Coming to the next part, how do we program it with orthogonal mechanisms? We have found that orthogonal mechanisms are not as limiting in practice. For example, the cluster-based scalable network server is a deployed example of the orthogonal mechanisms approach. Scalable Network Server is a software layer that provides high availability and incremental scaling on a cluster of PCs, but provides no persistent state mechanism facilities or data consistency guarantee. In fact, a programming requirement for SNS hosted applications, which are structured as composable subsystems in each application module, be restartable at essential arbitrary times. In SRM application, here SRM means Scalable Reliable Multicast applications. There are no hard copies of group or session state, but a soft copy is maintained by each peer in the session, and a multicast-based repair mechanism provides the basis of collaborative state maintenance. Crash recovery is based on refreshing the soft state via the repair mechanism. Similar techniques have been used to prototype a real-time streaming media server using soft-state protocol modules running on scalable network servers. What are the uses of orthogonal mechanisms? Composition of orthogonal subsystems shift the burden of checking for possibly harmful interactions from runtime to compile time, and deployment of orthogonal guard mechanisms improve robustness for the runtime interactions that do occur by providing improved fault containment. The practical implications of these effects is that application writers need not concern themselves directly with the provision of incremental scaling and high availability. The simple mechanism is server scalable network servers performs these functions for all applications. Various forms of sandboxing, including stack overrun guarding, system call monitoring, and software fault isolation, constitute good example of orthogonal safety. Orthogonal approaches are particularly useful in adding operational features such as security and robustness to legacy applications that were designed without these features in mind, without requiring special changes to the core application code. Specific mechanisms we have been able to exploit to simplify engineering and improve robustness or scalability includes simple mechanism with small state spaces whose behaviors are easy to reason about. time-based partial failure handling, guard timers, orthogonal security, and etc. Inspired by orthogonal mechanism in safety critical systems. The replacement of hard state with refreshable soft state, which often has the beneficial side effect of making the recovery code the same as the mainline code. The load balancing manager in Scalable Network Server works this way, using refreshable soft state mechanism inspired by IP multicast routing and scalable reliable multicast state repair. Simple techniques were chosen in order to simplify the formidable programming tasks, and techniques with good fault isolation were favored in order to preserve the fault isolation advantages already inherent in clusters. Finally, let's discuss few things what we went through and research agenda. We presented two implemented examples of mapping harvest degradation onto specific mechanism that provide engineering tractability availability through redundancy or some other desired operational feature. Simple mechanisms with small state spaces. The orthogonalization of these mechanisms with respect to application logic separating the application functionality from the provision of high availability. The replacement of hard state with refreshable soft state. Overall tractability of large-scale engineering involve hardware replications and redundancy. It remains to formally characterize applications that tolerate graceful harvest degradation, including as a special case those applications composed of degradation intolerant and possibly orthogonal subsystems. This comes to the end of our project. Thank you.